First, I want to thank the organizers for inviting me. I'm from RenLab at UT Austin, and today I will talk about our recent work on understanding the selectivity of calcium and magnesium using free energy calculations. So calcium is a versatile messenger in cell signaling that controls various biological processes, including cell growth and death, and metabolism, and muscle contraction. Because calcium is involved in different mechanisms at the same time, the calcium concentration must be precisely controlled by a large family of calcium sensors and buffers. So this is what a calcium binding protein looks like. The most common calcium binding motif is called EF-hand. It is highly charged with 3 to 4 carboxylate groups in the binding site. And the geometry is a well-defined pentagonal bipyramid geometry. The calcium binding proteins have very high selectivity for calcium against competing ions such as magnesium. The binding affinity for calcium is around nanomolar and micromolar for magnesium. The EF-hand binding proteins also have a high selectivity for calcium against strontium and barium ions. There are also exceptions that doesn't have this high selectivity, which I will talk about later. This high selectivity for calcium is actually counterintuitive because magnesium is a better charge acceptor, so it should be expected to bind more tightly to the highly charged pocket in calcium binding proteins. There have been quite a lot of work on understanding this mechanism for the selectivity, which are summarized in these review papers. One argument is the salvation penalty. Because the magnesium has higher salvation penalty, it should bind more weakly to the proteins. But this argument cannot explain why the selectivity can be finely tuned in the proteins. Another argument is that because many calcium binding proteins have the pentagonal bipyramid geometry, which is favorable for calcium. But this argument is not universal because there are also proteins without this geometry that can also favor calcium. So the mechanism for the selectivity of calcium is still unclear. We propose that this calcium selectivity is due to the many-body effect. For a molecular system containing multiple fragments, if we sum up all the pairwise two-body interactions between all the fragments, the sum of the two-body energy is usually not equal to the total interaction energy. And this correction term is what we call the many-body energy. The many-body energy is not a new concept, and it may not be significant for non-covalent interactions, but it is critical for the binding of divalent ions. And these are the results from quantum mechanical calculations for the two-body energy and the many-body energy for the calcium binding pockets. The difference is between magnesium complexes and calcium complexes. So the difference in the two-body energy is huge compared to the difference in the salvation energy, which means the two-bonding energy is always favorable for magnesium. And this is where our intuition comes from. But after considering the many-body interactions, the total interaction is much closer to the salvation energy. So consideration of the many-body energy is very important for the selectivity. This is a correlation between the many-body energy from QM calculations and the amoeba polarizable force field, which shows the many-body energy can be mostly captured by the polarization. So by considering the many-body effect, the polarizable force field can reproduce the experimental binding free energy. And this is the relative binding free energy between magnesium and calcium bending. This negative number means it is favorable for calcium. So these are the results for a bunch of different proteins, and the correlation is pretty good. The selectivity depends not only on the number of the charged residues, but also the arrangement of the carboxylic groups. For example, two proteins with the same net charge but different arrangement can have very different selectivity. For this 2C3 protein, which is the chemotaxi protein, the carboxylic groups are clustered together so that they cannot be closely bound to the metal ion. So it is very different from the other proteins. So this is the correlation between the calculated results and the experimental results. And on the right is the calculation without the polarization effect. It can be seen that without polarization, the calculation will result in the different selectivity. The calculated results are all positive, but the experiments are all negative. So including polarization is critical for the calcium selectivity. The question then is how to understand the many-body effect. In the gas phase dimmers, both the electrostatic energy and the polarization energy is favorable for the bending between carboxylic group and the metal ion. But in protein ion bending, the electrostatics is still favorable, but the polarization becomes unfavorable compared to hydration. And this non-additivity is the many-body effect. Because the many-body effect can be considered as the dielectric screening, it is always repulsive. If we subtract the hydration enthalpy from the bending enthalpy, we will obtain negative number for the electrostatics component and a positive number for the polarization component. As the ion size increases, both interaction will weaken, but the polarization energy will decrease much faster. So the total effect is a decrease of the free energy with the ion size. And this is why the larger calcium ion will be favored. And without the polarization, the smaller ion will be preferred. And this is why we have seen the different behaviors of the polarizable force field and the non-polarizable force field. And if this trend is true, we will see that the larger ion will always be favored. So I studied the set selectivity for a series of artificial ions in the bending process. It turns out for the rigid pocket, there's a minimum in the bending free energy, which is optimal for calcium bending. But for flexible bending pockets, the free energy decreases monotonically with the ion size. And for the pockets with weaker many-body effect, the selectivity is also weaker. And the existence of the minimum in free energy is consistent with the experiment for the EF-hand bending pockets. And so this ion selectivity is a result of a combination of the many-body effect and the geometric constraint of the pocket. In summary, the selectivity for calcium over magnesium in highly charged bending pocket is due to the many-body effect, which is more favorable for calcium. And the many-body effects are stronger when there are more charged residues and when they are densely packed. The ion selectivity can be fine-tuned by utilizing the many-body effect and the geometric restraint. I want to thank the Ren Lab and our funding resources.
It looks like you had a systematic stabilization of like 2 kcal per mole on pretty much all the predictions.
Yeah.
Clear that something you have any thoughts on?
Yeah, we have looked at the our force field, and it seems the binding energy between magnesium and the protein residue is too strong. So fixing the parameter may help with that.
Yeah. I was just wondering if you looked at the protein calprotectin, and if you haven't, you might want to look at that also. It's got a very unique 6 histidine complex with calcium. I think it binds those super. There are overestimations that might be amplified there, and it might help.
Yeah, that's true.
What parameter are you using for magnesium?
We're using a parameter that I optimized in my paper that I published last year. And it is based on the hydration free energy and the QM interaction energy in gas phase.
Did you read that your colleague gave thermalized paper on magnesium and came out like last year, so gas substantially different? It's like a very big change in the radius.
Which parameter are you talking about?
They thermally wrote this paper last year in JAX, the magnesium.
But this is for the amoeba force field.
Yeah, I was wondering about the like effective size difference. I don't know if they're fundamentally very different.
Thank you.